And the other thing I'm going to do is hop right into the slides and show some of the slides. Now, last time I was a little discombobulated, as I seem to tend to be. Somehow I had some set of slides that were a little different than I wanted them to be. I don't know how I messed that up. And if you were following along with the slides that had been posted on Moodle, you might have noticed there was a few discrepancies in the ones I was showing on the PowerPoint compared to the ones that were posted. Well, I finally got that straightened out. I have the correct slides, and I had missed a few that I thought were interesting. So I want to go back into things we've already covered a little bit to backtrack onto a few of the slides that I had left out when I was doing my presentation before. So again, I'm leaning in here, and what I'm leaning in to do is hit the Present Now button. And when I hit the Present Now, I'm going to present my entire screen, and then I'm going to click on my Present the Screen thing, and hopefully it's going to let me share my screen with you. And then when I do that, hopefully I'm presenting my screen, but hold on. That's not what I wanted to do. I wanted to do this. Okay, now I have my slides up here, and I don't know if I'm presenting my slideshow. I hope I'm presenting my slideshow when I hit slideshow from the current slide. So hopefully now you are seeing a slide that says classical mechanics, the old science, and the rest of it's blank because it's generating animated little statements that I'm going to make during the course of this slide. Okay, so if that is correct, or if it's not correct, somebody please just say, hey, it ain't doing what it's supposed to do. So anyways, what we're going to do is, as I mentioned, I'm going back into my slides, a few slides back from where we actually finished on Wednesday, because somehow these slides weren't in the package of slides I was showing. These say something about what had to be done. And remember let me maybe set it up a little more cleanly. We are trying to discuss the ideas as to how scientists figured out what atoms were like. And it was a long, involved process that people argued vehemently about, and ideas were tossed around and suggestions were made, many of them wrong, many of them partially correct, many of them had to be modified, but ultimately they settled on Rutherford's planetary model. And the planetary model is very familiar to us all. It's the cartoon you see in all the textbooks on physical science. It shows the nucleus in the center of a sort of solar system where most of the mass of that atom is concentrated in that nucleus. That's where all the positive charge is, and the positive charge is held in the nucleus by the neutrons. And then orbiting in small bodies at vast distances on the scale of the size of the atom, at vast distances from that nucleus, just like our solar system, there are orbiting satellites. But the orbiting satellites are not held gravitationally to the central sun as they are in our solar system. They are held electrostatically, or by opposite charges being attracted. So the electrons orbit the central nucleus just like the planets orbit the central sun. Now, the problem with that model was a couple-fold, and mainly it was due to the fact that charge accelerating, which is what happens if it's curving around an object, that must make the charge radiate. It must give off a form of light. Now, it might not be visible light, but it will be a detectable form somewhere in the spectrum of light, maybe somewhere in the radio waves, maybe somewhere in the X-rays, but somewhere in this broad range of wavelengths over which light acts. They should be able to detect radiation from an accelerating charge moving circularly around the nucleus. They couldn't find it. Secondly, if it's radiating, it's losing energy. If it's losing energy, it's slowing. If it's slowing, it'll get pulled in towards the nucleus, just like any satellite orbiting the nucleus gets pulled in if it slows its orbit as it goes around the sun and around the earth. Even when we have satellites spinning around the earth, they eventually crash into the earth when they slow down enough that the earth's gravity pulls it in faster than it's flying around. And the same thing would be true for electrons, so they should ultimately crash into the nucleus. There's no evidence of that occurring. So they had to modify the model of the planetary picture that Rutherford had come up with, and they literally had to invent an entire new way of thinking. Because at the time of Rutherford, what physicists used to describe the behavior of matter was what is now known as classical mechanics. And finally, I've reached the point where I'm discussing topics on this slide. This was the way we thought about the behavior of the physical world before the 1920s. And the main idea of classical mechanics are as follows. Now, first of all, what we now know. We didn't know this between 1700 and 1920, but what we now know, and this, one of the reasons I wanted to go back to this is that one of my multiple guest questions on our little section that we are supposed to do asks a question with regard to where does the old science of classical mechanics fail? Where did we now learn it didn't work? We now know in 2020 that the ideas of Newton, which were formulated in the 1700s and were used to describe the behavior of everything up until the beginning of the 1920s, the rules of that Newton had figured out, we now know don't work for very small things like atoms, like what we're talking about, but it also doesn't work for very massive things like black holes. As a matter of fact, Einstein predicted the existence of black holes when the gravitational pull of objects is so great in space that literally they affect what space is. It's really crazy stuff. You know, we're really not in a position to talk a lot about what goes on in this point number 2 that I'm making. All I will say is this. One way we can envision a model of gravity that incorporates these ideas is, let's just say space is a bed sheet. And then we have four people standing in the corners pulling very tightly on the bed sheet. And let's just pretend for a moment that bed sheet represents space. Now, if we want to get into the issue of what is space, that's deep and out there, but let's just pretend for the moment that we have 4 people in the corner of a bed sheet and they're tugging very tightly, so the bed sheet is really stiff and straight, kind of like a drum head or a trampoline would be. Now, when you put objects in space, according to the idea that Einstein proposed, objects with mass affect space. This is getting bizarre. And if you put an object into space, it starts to make divots in the space. So when you put an object into the universe, the gravitational pull of it bends space. And you can kind of think of this in the model that the sheet starts to sink. Now, if I put a golf ball on the sheet and I put a tennis ball on the sheet, they're not going to sink the sheet when people are pulling the corners to a large extent. But now if I put bowling balls on the sheet, I think we can all envision there's going to be pockets of dents in the sheet where the bowling ball is sitting. Einstein predicted that's kind of what very massive objects do when they exist in space. They bend space. They make divots in space itself. And one of the things he predicted is that when light travels through space, it's going to be going in a straight line. But if it approaches one of these divots that are created by a massive object, it'll bend and it'll fall into the divot. And we had never thought to look for this before, but when Einstein made this prediction, they went out and looked, and by esoteric experiments, they were able to say, yeah, we see that. We see light falling into a divot when it's passing a massive object in space. Well, black holes are so massive that when the light comes towards them, they fall and plummet in and never can make their way around it. They literally are trapped by the incredible gravitational pull of the black hole. That's why they call it a black hole, because no light can emanate from it, because it's all gravitationally sucked into the black hole. Okay, so that was a digression, and I apologize, but I think it's kind of cool. So I like to talk cool things, and if you think I'm just rambling along, you ought to see me after 2 or 3 drinks in the bar. Then I really get going. So in any event, we now have concluded that the ideas of Newton were great. They worked great on most things, but they didn't work for atoms. They didn't work for black holes. And lastly, the last place they didn't work were for things moving fast. And when I say things moving fast, I mean crazy fast. Crazy, crazy fast. So fast that we normally don't experience that speed. So we never, again, saw anything like this. So we didn't have to build it into our models of understanding because we never go that fast. Again, this is the genius of Einstein. Much like the middle one, number 2, the black hole thing, Einstein made those predictions. He made these predictions for number 3. That if things start moving fast enough, stuff is going to happen. And what is going to happen is really nuts. If you approach the speed, okay, well, maybe we should start here. The speed of light is the speed limit of the universe. Nothing, and I repeat, nothing in our universe can go faster than the speed of light. So nothing can go any faster than that. But when objects approach the speed of light, weird stuff starts happening. Weird. 1, things get very massive. They start to get infinitely heavy. 2, length starts to dilate. Things start to get crazy big in dimension. So they start to expand in size as well when they are moving near the speed of light. And 3rd, and maybe the most weird of them all, as things approach the speed of light, their sense of time dilates, meaning time sort of slows down. Now, for you in that frame of this, you're going at that speed, time seems normal. But if you got into this speed of light mode, when you stop moving at the speed of light, you will notice that time around you had gone very far along. So your time is slowed down relative to everybody else outside of your motion's time. So what might have seemed like only a minute for you, to the people around you that aren't moving at your speed, thousands of years would have elapsed. As crazy as all these things sound, the physicists of today have been able to verify that these facts are true. So these are the failures of Newton's ideas, and we really only found out about them when we were able to look at very limiting cases that we normally don't exist at in any ways. So Newton's rules work almost perfectly for most of the things that we care about, and these are only the limits of our understanding of the world about us, around us, these 3 places where Newton's ideas are no longer applicable. Now, another of the big failures of Newton is that he thought that energy was like this, like a ramp. And I talked a little bit about, I did mention this when we met on Wednesday. Energy being like a ramp means I can go up in energy or add energy by any amount I want. I can go down in energy by any amount I want. And we call increasing energy absorption of energy. And we call when we go down the ramp, when I emit energy, I'm going to call that emission of energy. And energy is conserved in our universe. If I put energy into an object, it must go up. If I remove energy out of it, it must come down in energy. But that energy has to go somewhere in the universe. So if I expend energy, I can give it to another object, but I am losing the energy I give it. If the object expends its energy, it can give it to me. And then it's transferred to me in the form of maybe light, in the form of heat, in the form of sound. But in some way, when it's transferred to me, the object that transferred energy to me has less energy than it originally possessed. Now, according again to the ideas of Newton in the 1700s and up until the 1900s, we thought energy was, as we're showing here, continuous, meaning you can go up any amount you want, you can go down any amount you want. Well, what we actually found out in 1920 when quantum mechanics became the way to think about energy is that, and I mentioned this again on Wednesday of last week, I didn't have a picture to go along with it. Energy is more like this. It's more like a stairwell. There's individual energy levels, and not any input amount of energy can get you hopped up enough to go to the next level. There's a distinct fixed amount of energy to go from each level. So energy comes in fixed, definite amounts like a staircase. Now, the reason it took us until the year 1920 to figure out that this is really how energy is distributed is the height of these stair steps. Excuse me. The height of these stair steps is minuscule compared to you or I. But to electrons, protons, atoms, this is a massive amount of energy. This is a measurable amount of energy compared to the amount they contain. So these are sizable steps for atoms or electrons. These are easily traversed steps for you and I. We're looking down upon these steps and they're so tiny that the staircase does look like a ramp. So to you or I, looking down at this staircase, the steps are so tiny that it is a ramp to us. But if you're an electron, you would be trapped in the pocket of one of these steps, and you would be looking up at the top of it, saying, wow, I need to input a lot of energy to get up to the next step. But again, to you or I, these are minuscule amounts of energy. So again, you can absorb energy and go up. You can emit energy and go down, but you must absorb or emit a fixed amount of energy. No varying amount, a certain amount that can be measured. And this was easily verified when scientists went and looked at the energetics of atoms. They found that atoms only emitted or absorbed certain amounts of energy. They couldn't absorb any amount they wanted. Every atom had characteristic amounts that it would like to absorb or emit, and it verified in the scientific model that this was the way energy was distributed in subatomic particles. So we had to modify the scientific method to include this behavior for tiny things, in addition to our normal thinking of how billiard balls behave, bowling balls roll around, and footballs fly through the air like they did yesterday when Tom Brady was defeated. Ha ha. Okay, now what I'm going to do is just, there's several words here, and I said some of these words to you already, so I'm not going to belabor them again. For you and I, the height of these stairs is minuscule. To an electron or an atom, the height of these stairs is massive. So it takes it's a measurable amount of energy to put into an electron or an atom. It's an immeasurable amount of energy to put into you or I. Okay, now I did these slides, so again, I'm skipping those. I'm skipping, I did all these on Monday, or I'm sorry, Wednesday of last week. I talked about the individuals who were named after slides. I talked about modern symbols. I talked about the Greek and the Roman symbols. I talked a lot about lead, if you remember. If you didn't tune in on Wednesday, I do have that taped, and I am going to post it when I get this one to post as well. So I'm not going to do that discussion again, but I am going to show this slide because, again, in my packet of last Wednesday, somehow this one got omitted. This guy is known as the father of the periodic table. His name is Dmitry Mendeleev. He was a Russian scientist. You can see he lived in the mid 1800s to the very early 1900s. Now, what I would point out to you is that Mendeleev died before quantum mechanics was fully understood. So he did not have the ideas of this new science to help him understand how to structure atoms. But he came up with his own model to put atoms in a collection to show how they reacted. At the end of the period last time, I had shown us the periodic table. But I wanted to bring these slides back because he's the guy who made that ubiquitously shaped table. Now what I'm going to do is pop ahead just to show it. There it is. This is the periodic table. This is actually the slide which we had ended our discussions on Wednesday upon. We were actually on this slide. Now, the reason I'm backtracking a little bit again is because I want to introduce to you the individual who's responsible for this shape. Now, I had mentioned again on Wednesday, but I will mention again that every time you see the known elements that humans now understand exist, you see them displayed in this format. And as I mentioned on Wednesday, this format was not chosen because a focus group decided, hey, this is catchy, and this is what advertisers would use so that people will recognize that we're talking chemistry when they see the periodic table of elements laid out in this particular fashion. Every box that you're seeing here represents one of the known individual elements. This is a little bit dated of a table. There are now about 114 of these known elements. They are always arranged in the format that you're seeing in this particular picture. And the person who came up with this format was this dude right here, Dmitry Mendeleev. Now, again, I will point out he did not know anything about quantum mechanics when he laid this out, but he did know about how chemicals reacted, and how he was deeming to lay out the table was based on the reactivity of elements. It was well known that there was repeating patterns of chemical behavior. Many people tried to correlate the behavior of chemicals or elements into a pattern, but the patterns just weren't fitting. It was known, they could figure out that hydrogen was at the beginning, it was the lightest element, and then helium was the second lightest element, and then lithium, sodium, boron, carbon, oxygen, nitrogen. By the 1800s, they were able to figure out how much each one of these weighed. But what was noticed at the time in the 1800s was as you got bigger and bigger, their properties began to repeat. The behavior of silicon was much like the behavior of carbon. The behavior of phosphorus seemed very similar, not to silicon, but it was similar to the behavior of nitrogen. And then after a bunch more elements came around, then the behavior of arsenic was similar in behavior to nitrogen and phosphorus. Then after a bunch more elements appeared, they found an element named antimony, and it also had similar characteristics to nitrogen, phosphorus, and arsenic. But it was way, way bigger than them. So what was recognized was there was a periodic behavior. It was known that the mass of the elements increased according to how many protons were present, how many positive charges were located in the nucleus of each element, but still the properties of the elements repeated in the types of compounds they formed and the properties they exerted. So there was something going on there, and they couldn't figure it out because nobody could line the pattern up to the increase in weight perfectly. Mendeleev was able to do it. He did it very cunningly. How did he do it? Mendeleev was able to lay out the behavior by repeating them. And as I said, many people did this, but what he went so far as to say was, wait a minute, the only reason that no one has been able to order the behavior of the elements exactly is that there were missing elements. Literally, humans did not know all the elements yet. And this, again, was around the late 1800s. So in the late 1800s, Mendeleev said, the only reason they're not laying out perfectly is we're missing some things. And he said, literally, I can say we're missing 3 elements. If we knew these 3 elements existed, they would fit the sequential growth of the mass of the elements and still repeat the pattern of chemical behavior over and over again. So he literally predicted the properties and behaviors of 3 elements. Now, he didn't name them, but people went looking for them after he predicted their behaviors. One of them was found in Sweden and became known as scandium for Scandinavia. Then a couple were found in Germany, and they were named gallium. I'm not quite sure why that one was named gallium, but another one was named germanium, and that was after Germany. So Mendeleev predicted that there were missing elements that had not been discovered yet. And if we could discover these elements, I know exactly their properties. I know how much they'll weigh each atom, how much each atom will weigh. I'll know what kind of reactions it does. I'll know how heavy, how mass to volume density it exerts. I will know everything about it. It'll have to fit these properties because it fits perfectly now in this table that I can lay out. So again, when Mendeleev did that, the elements fell perfectly into place into this table. Now, I want to point out, and I got to put my little goggles on, which of these elements were the ones that Mendeleev had figured out. Element number 21 in box 21, that wasn't known. He just left a blank space there and predicted how it would behave. And then over on the other side, elements 31 and 32 weren't known. Now, these are relatively rare occurring elements. So the reason they hadn't been found yet is that there's just not a whole bunch of it on Earth. Now, it turns out all 3 of them are very important, particularly in the semiconductor industry, when we want to make all these incredibly important transistor circuits that make it possible for you to hold that little smartphone in your hand and for it to be able to do all the amazing things that it can do for you. If these elements weren't known, then you wouldn't be able to store the charge or move the charge around in the necessary fashion so that that cell phone can do all the really cool things that that cell phone can do. So in any event, I certainly wanted to give a shout out to Mendeleev because of the really crazy and cool trick he pulled. And let me point out to you once again how cool what he did is. How cool what he did is he said, everybody else is thinking inside the box, meaning everybody thinks we know everything already. Nobody's saying, well, there's just stuff we don't know. Nobody would go that far as to say that possibly chemists of the time were making mistakes. The mistake was that they didn't know that these three elements existed. He said, well, if I just make them up, then everything fits perfectly. So and believe me, he was to a certain extent ridiculed at first when he did this. People said, get out of here, you're crazy. And they didn't buy into this at all. But then shortly after he made these predictions, people went out and found these elements, and it just goes to show, with a little bold thinking, with a little outside the box thinking, a little beyond the norm thinking, he was able to make an incredible advancement in the science of chemistry. Okay, now, again, I did talk a little bit about these things. I want to mention them again because they're going to be important going forward. Each box represents one of the so-called elements. It's called the periodic table because the properties of the elements are periodic, meaning the property of the elements repeat. Every element in the same column, and each column is known as a group of elements, every element in the same column or same group has very similar chemical properties, meaning they undergo the same kinds of reactions as other elements piled in their group. Like, for instance, in group 14, carbon C, silicon Si, germanium Ge, tin Sn, lead Pb. All five of those elements have very similar chemical properties. For instance, if they react with hydrogen, they will make CH4, SiH4, GeH4, SnH4, and PbH4. Now, unlike their cousins next to them, if nitrogen, phosphorus, arsenic, and antimony, which is the next column over, column 15, if they react with hydrogen, they will make NH3, PH3, ASH3, and SbH3. Completely different chemical behavior with just an increase in atomic number of 1 compared, which, okay, maybe I should remind us, increase of atomic number of 1 means add 1 more proton to their nucleus, and they will then each in that column combine with a different number of hydrogens. Okay, so the groups of elements are called, the column of elements is called a group. Groups have similar chemical properties in terms of reactivity, and the reason it's called a periodic table is the repeating pattern, meaning element number 6 with 6 protons in its nucleus would form CH4. And then when you come back around to element 14, you'll form SiH4. And you come back around to element number 32, you'll form GeH4. And so forth, going down that column. Repeating pattern of chemical behavior. Lastly, I will mention that the word elements has resurfaced. The word element was introduced by Aristotle, and that was introduced years before the birth of Christ, but he thought the elements were climatic conditions. That's why people say, don't go out in the elements, you need a scarf or you need a coat, because you go out in the elements, you're going to get wet. Because according to Aristotle, the elements were air, earth, fire, and water. And you could build everything from those elements. Well, again, we return to the name elements, I guess maybe in deference to Aristotle, but they're nothing like the things he proposed as being the building blocks of matter. Okay, now what we then next talked about, we talked about these things before. I'm going to go a little quickly here. If we talked about the fact that protons and neutrons are way more massive than electrons, so the mass number counts how many protons and neutrons are present in an atom, and there's a 1-to-1 ratio, and again, I thought I fixed this too, but I guess I didn't, of neutron to proton. That's what that should say, neutron to proton in the so-called light nuclei. Now, what are the light nuclei? if I look in my table, I'd say the first 3 rows going across to say element number 36. I guess that's 4 rows. Element number 36, that's like krypton in the table. That's what we would call the lighter elements, the first half of the table, essentially. And for every proton in the nucleus, there's a neutron in the nucleus. Like beryllium is element number 3. That means it has 3 protons. Well, it has 3 neutrons to go along with them. Say fluorine is element number 9. In a fluorine nucleus, you're going to have 9 protons. You're going to have 9 neutrons. When you get further down the table, when you get to the heavier ones, they have more like a 1.5 to 1 ratio of neutron to proton. Something like lead would be in that category. And then finally, what we will, and I mentioned this again on Wednesday, this is all repetitive, if you like. If you have isotopes, they have the same number of protons, so that they have the same number of positive charges in their nucleus, but the number of neutrons might differ. And so many elements have different isotopes. And so then what we say, and we talked again about this before, is that they have the same atomic number, meaning the same number of protons, but different mass numbers, because the mass number counts proton plus neutron. Okay, so I had talked about this, so I want to move on here. Again, we're heading well into half the period being over, and we're still just catching up to where we were. A neutral atom, which generally most atoms are, that aren't in combination with one another. So if you have a jar of an element, the atoms of that element are invariably neutral. And when they are invariably neutral elements of atoms of an element, they have equal numbers of protons and electrons, equal numbers of positive and negative charges. So there is no, as we say, net charge. Most atoms that you have in a jar on the shelf are electrically neutral. But when atoms combine, they begin to trade and swap and share electrons among them. Electrons, or for that matter, protons or neutrons, are not going to be created or destroyed. They're just going to be swapped around when atoms react. And in particular, we're going to swap the electrons around. The protons are too energetically strongly bound in the nucleus. They're never swapped. So we define what we call the anion is the negatively charged atom, because electrons are negative and anions are negatively charged, meaning they have a buildup of electrons. So anion is a negative atom because it has piled extra electrons onto it. And I told you a few times now, you can make yourself into an anion by dragging your feet across the carpet. You scrape billions upon trillions of electrons out of the carpet, and you are literally making yourself into a negatively charged thing. Well, simultaneous to that, as you scrape those electrons loose, you are making the carpet a cation. And a cation, as it says at the bottom, is a net positively charged atom. And it is positively charged not by adding protons, that is too energetically difficult to do. A cation is formed by losing electrons. It loses its negative so that it is net positive. Okay, so this is showing you how you may see a representation of an element and how you should be able to determine how many protons, neutrons, and electrons that atom has. And I'm going to, on our little problems assigned to us, be asking you questions that you show me that you can do this. So let's be clear as to what we're doing in this particular slide, because again, on our next assignment that I'm going to be posting, you're going to be asked to be able to do something like this. Very often in chemistry or in material science, you will see a symbol like this, a number as a left superscript, and then a symbol of an element. This happens to be Zn, which is zinc. And to the left of the zinc in a superscript is given a number 65. The number to the left that you see, well, first of all, the symbol is telling you what element it is. And if you scan around in the table, and the table's kind of little, so I got to put my glasses on because I can't see, but I got to look around in the table. I see, oh, there's zinc. It's element number 30. So I see zinc is element in box 30. As soon as I see zinc as being in box 30, I know that zinc is in the box where atoms have 30 protons. So as soon as you can identify the symbol, you look at the table, you look sequentially at what the number of that box is, not the number at the bottom, but the number at the top. Now, if you want to know what the number at the bottom is, I can tell you it's how much the atom weighs. So if you're going to go to the scale and start scooping it out, the number at the bottom of the box is telling you how much you need to scoop out to get a representative pile of the material. But we're concerning ourselves, we're not going to worry about that. If we were taking a chemistry class, you would. All I'm going to ask us to be concerned with is the number at the top of the box. That's going to tell you the number of protons. So you should immediately be able to recognize how many protons the atom has. Now then, the left superscript number will help us find the neutrons. Once you find the protons, you turn to the left superscript. That is the so-called mass number. The mass number counts the total number of nucleons, or protons and neutrons. So if the mass number is 65 and the box number is 30, then I can subtract 30 from 65 and recognize that the number of neutrons in this zinc atom is 35. Now I said for the light atoms, it's about a 1-to-1 ratio of protons to neutrons. We're getting toward the heavier light atoms, so the ratio is going up slightly, but it's close to 1-to-1 for zinc. So that's where the nature of that idea comes in. Now, we have been able to determine from the atomic number and the mass number the protons and the neutrons. How are we going to be able to determine the electrons? Well, we will look to see if there's a charge printed on the atom. If there's a charge printed, that will tell us something about the electrons. If there's no charge printed, we assume it's a neutral atom. And a neutral atom has exactly as many electrons as it has protons. So since this is element 30, it has 30 positive charges. If no charge is listed, I'm assuming it's got 30 negative charges to equally balance the positive charges. So if you see this symbol, you should be able to tell me exactly how many protons, neutrons, and electrons atoms of this element contain. Again, let's just do some further examples. This is the element O, which is probably familiar to pretty much everybody. That is oxygen. And what I will do to find out the number of protons in oxygen is dig around on the table that I'm showing you until I find oxygen. I find oxygen O in box 8. So since it is in box 8, that means it has 8 protons. I turn to the mass number. The mass number is 16, which is the sum of the protons and the neutrons. So I will take the mass number minus the atomic number and get the number of neutrons, and there are 8. So again, this kind of fits what I said earlier. For the light elements, there's equal numbers of protons and neutrons. You got to be sure, though, and check by subtracting the atomic number from the mass number. Okay, now let's talk a little bit about the number of electrons. Here, this element is listed with a right superscript. And the right superscript is telling me something about the charge. Since the charge is negative, what that means is that it has more electrons than it has protons. The imbalance of charge is given a sign. If the sign of the imbalance of charge is negative, the sign imbalance tells you you're tilting towards electrons. If the sign of the imbalance is positive, you're tilting towards protons. So this is -2, it tells me I have 2 extra electrons compared to protons. So the charge is -2, 2 extra electrons. Since there's 8 protons, this must have 10 electrons. Essentially, we're saying 8 of the positive charges cancel 8 of the negative charges, but there's 2 extra negative charges left over behind that aren't canceled. Okay, just a couple more examples here. If we saw this calcium with the left superscript 40, that is a +1. Now, I guess I'm doing this quickly, and I don't have the table, so I'm just going to come back to the table and show you. The box of calcium is in box 20. In the table, it's box 20, and so I know immediately there are 20 protons in the calcium nucleus. Now, the mass number is 40. And since the mass number is 40, that means there is 40 minus 20, or 20 neutrons in the nucleus of calcium. So then lastly, we have to determine the third subatomic particle, which is the electrons. Now this is a +1. Now what the uninformed might take from that is that this must have the number of protons of calcium plus 1 proton. That is not true. This does not have 21 protons. If you have 21 protons, and I'm backing up here and I'm putting my glasses on so that I can see that the box next to calcium is scandium. And the box next to calcium's box is box 21 and has Sc. Only an Sc atom has 21 protons. All calcium atoms have 20 protons. So to be a calcium, you must possess 20 protons. Well, what does this +1 then represent? What it represents is an electron deficiency. Electrons are less energetically bound to atoms compared to how protons are bound. You can't reach into nuclei or shove protons into nuclei because that is energetically massively costly. As a matter of fact, you would have a nuclear explosion if you began to fool around with the number of protons in the nucleus of an atom. However, on the other hand, as I've mentioned several times now, it is energetically cheap to start pulling electrons off. And again, your mom and them do this every day when they scrape their feet across the carpet. So anytime we make a cation, which is a positively charged entity, we will make it positively charged not by adding protons, but by removing electrons. So since this is calcium with 20 protons, in order to make it a +1 charge, I will remove 1 electron and make it 19 total electrons. Okay, now here are just some other examples. What I would suggest, rather than me spending 5 minutes discussing this answer for zirconium, you should get the table on the previous slide and verify for yourself the number of subatomic particles, that there are 40 protons, 51 neutrons, and 43 electrons based on the rules we have discussed. And if I had hydrogen 2, which is called deuterium, such an important used material, we actually name this one deuterium. It actually has basically its own atomic name. It's still an H, so it has 1 proton, but it is an isotope of hydrogen that has a neutron in the nucleus with that proton. And because it's neutral, it has 1 electron as well. That is opposed to this isotope of hydrogen. This one is known as tritium. This one turns out to be radioactive. meaning it has an unstable nucleus. I talked about nuclear stability a little bit last week. And it turns out when you start piling too many neutrons into a nucleus, just like trying to pile too many positive charges in, now piling too many neutral charges in also upsets the balance in the nucleus. This is a radioactive isotope of hydrogen. It has one proton because it's H, but now the mass number is 3, so it has 3 minus 1 or 2 neutrons in tritium. And since there's no superscripted charge, it must have the number of positive charges as it has negative. And since all hydrogens have 1 positive charge, tritium has 1 negative charge. Okay, now, again, I'm not even going to go through these. I'm bored with doing this. I do suggest that you make sure that you could get these answers for these particular isotopes of phosphorus and manganese. Because, again, when I post some problems for you to do, I will have a picture of a periodic table to help you, but you should be able to write down for me the number of protons, neutrons, and electrons each one of those isotopes would possess. Okay, now what we're going to move into is something that it's quite possible you spent a little bit of time discussing if you took Physical Science 101, but that does not bother me if you did, because I probably tell the story better because I'm me, but also because when we unraveled the structure of atoms, the use of electromagnetic radiation in doing that unraveling was very, very important. So again, it's quite possible that you spend a decent amount of time talking about the behavior of light in your last class of this type that you took. I'm just going to say, I want to say some things about light in our class because of its importance to interpreting and understanding what kind of matter you have. We can't look at an atom individually and see it because it's just so tiny. So what we had to do and how we ultimately unraveled this atomic structure was we shined light on atoms. And it was what happened to atoms after light impinged upon them that led us to our model of interpreting the structure of atoms. So, as I say here, the probe that scientists used to determine the manner in which electrons are distributed in atoms and molecules was so-called electromagnetic radiation. So, I already mentioned that Rutherford thought there was a planetary model, that electrons just buzzed around the massive nucleus, much like orbiting planets around the sun. Again, I mentioned several times now that physicists didn't like that explanation because charges that are moving circularly are accelerating. Accelerating charges must radiate or give off some form of electromagnetic radiation themselves, and they must lose energy. So when doing this, they would both emit some form of light and eventually crash into the nucleus as they do that. There's no evidence that this occurs, so they had to modify the planetary model. So they were shining light on atoms and noticing that hydrogen absorbed certain kinds of light. Oxygen absorbed not the same kind that hydrogen absorbed, but completely different kinds of light. Carbon dioxide absorbed even different kinds of light than either hydrogen or oxygen. So it was this behavior that atoms and molecules exerted towards different types of light being shined upon them that led them to unraveling the weirdnesses of the structure of quantum mechanics. Okay, so what is electromagnetic radiation? That's what we call light. But it's just a broader, more general term for the many components of electromagnetic radiation that are all very familiar to us. Now, the reason we use the word light is that is what more correctly I would call visible electromagnetic radiation. So for our discussion over the next couple of days, when we mean light, and your mom and them, of course, are familiar with the term light, we will mean visible electromagnetic radiation, which it turns out, as we will see, is just a very small fraction of the entire so-called electromagnetic spectrum. Okay, now what is electromagnetic radiation, or what is light? Electromagnetic radiation, as it says here, is a propagating transverse wave consisting of an electric and magnetic field which are 90 degrees opposed. Okay, lots of big words here. Let me try to describe what they mean. The idea of electromagnetic radiation being a propagating wave means it's a wave that moves through space. We can think of an analogy of dropping a rock in a pond. It creates a disturbance in the pond, and now waves emanate outward from the point where the rock was dropped. Now, we're very familiar with this pattern of waves. It seems to be kind of a regularly repeating pattern. It's kind of a tailing off pattern, meaning close to where you drop the rock, the surface of the water undulates upward and downward to the most extent. And as you get further away, the ripples from the rock seem to fall off until they disappear. So the reasoning behind this is that the wave loses energy. To create a disturbance of the surface, and we'll just consider the water surface as being completely flat, now I'm undulating the surface, moving it up and down below the flat point. So there are troughs that are lower than the normal surface height, and there are peaks of the wave which are above the normal surface. Well, to move this water up and down above and below the surface requires energy. And of course, where did that energy come from? It comes from when I drop the rock, from gravity. It's transferred from gravity and mass of the rock to the surface of the water, and it undulates the surface of the water. But now, as this undulation propagates from the point of the disturbance, the energy dissipates or is sucked out by the surface, and the waves slowly die out. We're all very familiar with that. Now, what it means to be a transverse wave is kind of interesting. What that means is the surface has undulations, as I said, above and below. Peaks and troughs, the surface moves. But those are, as we say, perpendicular to the motion of the wave. Perpendicular means 90 degrees away from. Here's what I'm getting at. When you drop the rock, the surface of the water moves up and down. But the wave doesn't move up and down. The wave moves out on the surface. So as the surface goes up and down, the wave is still moving away from the point. So it's going woo, 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 and dying and getting smaller and smaller. So it starts big, slows, as it moves away from the point of generation. It's a transverse wave because the motion is up and down on the surface, but left to right across the pond. That's what we mean by that. And the reason we call it electromagnetic radiation is that it's an electric and a magnetic wave. meaning it has an electric piece to it and a magnetic piece to it. So all light has an electric part and a magnetic part. Now you probably, maybe you talked about electricity a little last semester. Maybe you talked about magnets a little bit last semester, but I certainly don't expect us to have some great understanding of what they are. Electric, we've talked a little bit about already. It's this weird, attractive, or propulsive push or pull that charge exerts on each other. So anytime you have charge, it can push or pull on other charge. It pushes on charges which are the same as itself. Like charges repel like charges. Positive charges push other positives away from themselves. Both of them push equally on each other. Opposite charges pull each other towards each other. Plus pulls minus towards itself, minus pulls plus towards itself. Now, what's the idea with electricity? It's weird. And again, maybe you talked a little bit about it last semester. We're just going to say a few things about it now. We might return to it later, depending on what we got going on towards the end of the semester. What we need to know about magnetism right now is that it is charge in motion. Charges sitting still have electric attractions. Charges moving make magnets. So when you have a little magnet that you can pick up nails with, it is making a so-called magnetic field, because if you could look down inside the atoms of the material that make up that magnet, they have moving charges that are unbalanced, and their motions work collectively together, not canceling one another. They work together to make a little magnetic tug. Now again, in order to make magnets, you need charge, and you need moving charge to make a magnet. So once a charge starts moving, it starts to make a magnet. And interestingly, they're regenerative towards one another. If you move magnets, you make charge. If you move charge, you make magnets. So this is the nature of electromagnetic radiation. It starts with a charge moving up and down an antenna. So that's where we can think of it emanating from. I want to send a radio signal through space. I get a big, tall metal conductor that allows charge to flow in it. I put a current onto the metal conductor, and now charge begins to run up and down through the conducting metal, through the antenna. That means charge in motion makes a magnet out here in space. And as the magnet moves, it makes charge moving through space. And then the charge moving makes magnet. Magnet moving makes charge. Charge moving makes magnet. And the electromagnetic radiation is the disturbance in space of electric and magnetic. Electric and magnetic. So unlike making a rock disturbance in water, I'm making a space disturbance with magnets and electrical charges. And this is a cartoon of electromagnetic radiation propagating through space. It's kind of weird, I agree, but this is kind of how we think about what's going on. This is our model of it behaving. Notice how I have arrows going up and down and up, and I have arrows going left and right, right and left. The up and down and up arrows are my electric field generated by the moving magnet fields. The right and left arrows that I'm trying to show for this propagation are the generated magnetic fields by the moving electric fields. So as electromagnetic radiation goes through space, I have a positive electric and then a negative electric and then a positive electric, and then a negative electric. That's an oscillating so-called electric field. As that is being generated simultaneously, I have a generated magnetic and another generated magnetic. We don't call those positive and negative. What we call those is a north magnetic field, a south magnetic field, a north magnetic field, a south magnetic field, in terms of the name given relative to the behavior of a compass if it was brought into proximity. So when we move charge through space, we begin the propagation of a wave. Now, if it's in the visible regime, it'd be a visible light wave, but it could be many other forms. There are a whole bunch of forms of electromagnetic radiation, once again, given names I'm sure you have heard of. The wavelength of light is how long it takes one wave to completely undulate. So here's a cartoon showing the oscillation of this electric, or oscillation of this magnet as it travels through space. It goes from a maximum positive down to zero. Then it goes down to a negative trough, back to zero. Then to a maximum positive, zero. Maximum negative, zero. And it keeps doing this as the wave moves through space. Now, what you should liken it to is the water wave. I drop the rock, I go down, and then the water surface bounces up. Then it goes down, then it bounces up. And as it does this, it moves away from the point of the disturbance. And as it does this, the amplitude of the wave dies. Now, what is the amplitude? You can see it on my cartoon. It's the height of the disturbance. So one of the things you should take from this is, like for a water wave, if it's got big amplitude, it takes a lot of energy to generate a big amplitude disturbance of the wave. The more energy it has, the bigger this amplitude is going to be. Now, if it's a sound wave, it's the same thing. A sound wave with big amplitude is an indication of, very familiarly, the loudness. The louder the sound, the bigger the amplitude of the sound wave. So this undulation of the surface, particularly in water, I think we can get that same idea. I put more energy into the water wave, the undulation of the surface gets like a tidal wave. It's crazy big when I have that kind of situation. So this change of height of the wave is a function of what's known as the amplitude of the wave, and it's the height of the disturbance matched by the trough of the disturbance. Now, for light waves, it's very interesting. The peaks and troughs are all the same amplitude. So the upward swing is exactly matched by the downward swing. This is pretty much true for all waves, certainly the way we model them. We're going to model them so that this amplitude is matched up as it is down. Now that's in the vertical direction. So that's what gives it its transverse character. The height of the wave is how far above the surface you're undulating. But the wavelength is one complete cycle of the wave. So notice I picked out a wavelength from going from the first peak down to zero, down to the trough, back to zero. And when I return to the next peak, I have found one wavelength. Now the symbol that scientists use for wavelength is the Greek lowercase l, and the Greek lowercase l is a lambda. So this is pretty much the ubiquitous symbol that we use for measuring the wavelength of light. Now, it turns out that another model we employ for waves, which is very valid, is that the waves are very consistent. The wavelength is the same no matter where I measure it from. Meaning, I can start at the 0 point on the way down and go to the next returning 0 point on the way down. That'll have the same wavelength as going from the peak to the next peak. I can start at the trough, at the minimum amplitude. And when I come to the next trough, the next minimum amplitude, if I measure the wavelength between those points, it'll be exactly the same as it is for the peak to peak wavelength. So no matter where or from what part of the wave I measure the wavelength, it's always going to be the same. Now, another familiar term we use to measure the wave is its frequency. And these are often used interchangeable, as we will see. The frequency counts how many waves will pass me in a given second. So if I stand still and watch the wave fly by me, count how many come by me per second, that is known as the frequency of the wave. The shorter the wavelength, as we will see, the more come by me each second, so the higher the frequency. The longer the wavelength, the fewer that come by me every second, so the lower the frequency of the light. Okay, it looks to me like it's quitting time. You've been a great audience today. Hopefully on Wednesday we'll be back to the normal conditions. I will also be posting these things. I will be sending out an email announcement. I will be sending out an announcement when I finish the grading of the ones I had to grade by hand for the first part of the test that we took. So until next time, folks, peace out. See you next Wednesday, or this Wednesday. Not that one.